Let us introduce the disaster response robots developed at Kyoto University and Osaka Institute of Technology's Matsuno Laboratory. Our goal is to learn from living creatures, go beyond them, and create robots that solve real social challenges. Let's start with the snake-like robots. On the left, you see a sidewinder snake living in the desert. Our snake robot can move sideways just like this. On the right, you see a snake climbing a tree. It wraps itself around the trunk, lifts part of its body to make new anchor points, and climbs upward. Inspired by this, we designed motion of our robot to lift part of its trunk while climbing pipes and overcome obstacles. But simply copying snakes isn't enough. To handle complex environments, we made our snake robots with smooth surfaces to avoid snagging, and developed new control methods. By combining these basic movements, the robot can create a wide variety of behaviors. For example, it can come out of a pipe, wrap around it, and move along the outside. It can also wrap itself around a pipe and work on it at the same time, and it can climb ladders. This robot is wired, but the cable won't catch on the ladder rungs. That's one of its key features. To make robots work in real-world settings, it's essential to develop mechanisms that let them adapt and keep moving, even under unknown conditions. One such motion, called the crawler gait, lets the robot roll itself like a wheel and is great for rough terrain. It can also climb natural trees automatically. Next, let's look at our crawler-type robots. Compact but multifunctional, these rescue robots are expected to play important roles in the field. To test our robots' performance, our lab takes part in international competitions RoboCup Rescue World Championship. In these competitions, operators control the robots remotely without direct sight of them, and the robots need to handle rough terrain and perform dexterous tasks. We also joined the World Robot Summit Plant Disaster Prevention Challenge, which evaluates both daily maintenance and accident response in a mock plant. Our robots have achieved multiple tasks: opening and closing valves, performing AI-based automated meter recognition and data reading, recognizing panel displays with operational status determination, and detecting tank cracks. Here are some examples of how we've actually used these robots in real disaster sites. First, the Great East Japan earthquake of March 11, 2011. On the day of the disaster, we were at Disaster City, a disaster training facility in U.S., conducting performance evaluations of our robots. A week later, we returned to Japan and used unmanned ground vehicles in Hachinohe, Kuji, and Noda for search operations. 1 month later, in a Japan-US joint team, we used underwater robots in Minamisan Rikyu and Rakuzentaka to investigate debris and search for missing persons. The clip above shows an inspection of a gymnasium with a collapsed ceiling. The clip below shows the camera footage from an ROV investigating the inside of a car submerged at a depth of about 40 meters. Next is the landslide disaster caused by the 2018 West Japan heavy rain disaster. The video above shows the recovery of valuables from a restricted entry, partially damaged apartment. The 3 videos below show the inspection of the interior of a completely collapsed wooden house. Because major disasters often strike when least expected, daily preparedness is vital. These left side clips show our snake and crawler robots exploring a hidden passage in Osaka Castle's dry moat in 2022. These right side clips also show inspections inside pipes and daily maintenance of plant facilities. At Matsuno Laboratory, we are advancing research and development with dual use for both normal and emergency situations in mind, aiming to create harsh environment robotics. Thank you for your attention.